I am Emer Didi, chair of the Applied Mineralogy Group, which is a special interest group of the Mineralogical Society of Great Britain and Ireland. And in that role, I take as many possibilities to promote applied mineralogy and to support students and academics who are interested in applied mineralogy. To that end, I would like to point out that the AMG student bursaries, which are open to everyone, but preferably if you're a member of the Mineralogical Society, our next deadline is the 1st of March, which is very soon. I appreciate not everyone will be able to get to fieldwork, but maybe if there's some lab work you're able to do that we can help support, please do check out that link. I'll put all the appropriate links in the chat box when we get started. And our next Open Geoscience talk will be by Professor Eva Harty, and she works on combining geothermal energy and recovery of metals from that. And this is the third in our series of talks, and they've been very well attended. And again, I'll put the link for that in the chat if you're interested to come along. We are on Twitter. Most of the things we do are advertised that way, or on our web pages. Again, pop those links in. And just to note that you can join the Mineralogical Society as a student for free for 1 year, and otherwise it is actually excellent value to join. And if you look at our meetings or events page on our website, again, I'll pop the link in, or Kevin may already have done so. All of those links are available. All the list of all the meetings and everything at the moment is all virtual, and anyone from anywhere can join. So it is great. There's a huge amount of things there, especially in our back catalogue as well. I think that's all I have to say about AMG. So about this particular workshop, this came about because Dr. Michael Anenburg has produced some fantastic software for calculating lambdas for your rare earths. And he published this at the end of last year. And the feedback from that has been fantastic. And quite a few people were really interested, and this is how this meeting came about. So I'm delighted to have Michael here presenting that software. And then off the back of that, he also knows Dr. Morgan Williams, who produced the Pyrolyte Python package for geochemistry, which is fantastic. And then I also thought we should probably have a little refresher. So I'm delighted to have Dr. Marc-Alban Millet here from the University of Cardiff, who's going to introduce the rare earths to anyone who needs just a little refresher. I'm going to stop my share now, Marc-Alban, if you'd like to share your screen and get us all started. We do have a code of conduct for online meetings, so please be respectful of everyone. I'll put the details of how to ask questions in the chat box as we go along. Thanks very much.
Okay, hello everyone. So this is really much of a refresher to make sure that there's a wide variety of expertise here with using of rare earth elements in geochemistry. So it's just to put everyone up on the pretty much the same level, or at least give the basics to most people. So I'm just going to start sharing now. And so, yes, a quick refresher on rare earth elements geochemistry. So I'm Marc-Alban Millet. I'm based at Cardiff University. I'm also secretary of the Geochemistry Group of the Geological Society of London and Mineralogical Society as well. Okay, so it's a brief outline. So we'll be talking for about 20 minutes or so. So what are rare earth elements and why do we use them? And importantly, because we are going to talk here today about parameterization of rare earth element patterns, is actually why do we normalize rare earth elements and how do we do this, and sort of talk about some caveats around this. And then I'll quickly highlight two uses of rare earth patterns in petrogenesis, and mainly these will be high temperature examples. So I apologize for the low temperature geochemists around amongst you. These are mainly about high temperature geochemistry, simply by lack of time. Okay, so what are rare earth elements? So rare earth elements here are highlighted in blue in this scheme of the periodic table. This is a group of 15 chemical elements that are placed consecutively in the periodic table. And the key bit here is that these are elements that are fairly similar geochemical behavior and gradual variations amongst that. So these are elements that are grouped from the lanthanum, which is an atomic number of 57, to lutetium of atomic number of 71. You'll see sometimes in some literature, and especially on the more chemistry-focused literature, that two of the elements are associated with the rare earth, is that scandium and yttrium. We are going to leave them aside for today, but bear in mind that sometimes they can be associated with this group here. And another important point that I'd like to make right now is that one of the rare earths is actually not found in nature anymore, and this is promethium. And this is simply because the isotopes of promethium all have a very short half-life. So while you can find it sometimes, it's actually completely synthetic and laboratory impact. Okay, so why are actually rare earth elements a group? Okay, most elements are looked at individually, or some may be found as a group, but why are rare earth elements found as a group of 15 elements? And the reason for this is actually because of the arrangement of their electronic structure. Okay, so as the atomic number of chemical elements actually increases, we add protons and we add also electrons to balance the charge. And this means that we gradually fill what we call the electron orbitals. And this is done according to what we call the Kleshkovsky rule, okay, which is highlighted on the left-hand side of this slide here. So by hydrogen and helium, we'll fill the 1s orbital. And then we start growing up in the periodic table. And we start filling the 2s orbital, then the 2p, and we follow these arrows here, which are essentially the Kleshkovsky rule. Okay, so 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. Okay, and then we arrive to lanthanum and cerium, and then we're actually going to start filling up what we call this 4f orbital. Okay, and these f orbitals can actually hold up to 14 electrons. Okay, and so this is actually what filling up this 4f orbital is going to be the rare earth group. Okay, these are the elements that are found within this periodic table. This is this region of the periodic table. Okay, so I've highlighted here the electronic structures of lanthanum and lutetium, and you can see here the lanthanum has a slightly anomalous electronic structure. This is an exception to the Kleshkovsky rule, but the point here still stands that this is an empty 4f orbital, whereas the lutetium here has a full 4f orbital with 14 electrons here. Okay. And the fact that this gradual filling up of this 4f orbital results in broadly similar chemical properties, and the small variation in behavior is actually going to be controlled by these gradual changes in both mass and, more importantly, actually ionic radius. Okay, this is why these rare earth elements are always looked at as a group together. Okay. So when we're talking about ionic radius, and this is really the key property that's going to be controlling the chemical behavior of rare earth elements in geological system here. Okay. Importantly, as you know, what you would originally expect is that because with increasing atomic number, you could expect potentially that ionic radius is actually going to increase. Actually, it's the other way around for rare earth elements. And so why is that? Why do we have this decrease in ionic radius with increasing atomic number from lanthanum to lutetium? And then the reason for this is that because it's the nuclear force, which is exerted by the nucleus on the electrons, actually increases with more protons. Okay, we do have more protons there, the nuclear force increases. However, the electrons in f orbitals actually do not protect, or what we call also shielding. They do not shield the electrons from being attracted to the nucleus, as well as the lower orbitals as DNP. Okay, and the reason in that is that basically with increasing number of protons and electrons, then the nuclear force exerted per electrons is actually going to increase over this over the rare earth group. Okay, and this means that because this nuclear force is more important for per electrons for lutetium compared to lanthanum, for example, this means that they are going to be more attracted towards the nucleus, and yet ionic radius is going to decrease as a result. Okay, this key property here actually controls mineral partitioning in the larger sense. Okay, we do have, so this is represented here on the right-hand side with the ionic radius going from about 1.16 angstrom for lanthanum down to just under, so about 0.97 angstrom to lutetium. This is in a single coordination here. Depending on the coordination, this will be affected slightly, but all else being equal, this is the effect here. Okay. We do also have some exceptions to that, which is that most rare earths are actually trivalent, so they have formed 3+ ions. We do have 2 exceptions there. Cerium 3+ can be oxidized to Cerium 4+, and this is mainly in sedimentary system and in seawater, for example. However, this can be present in some magnetic system. For example, zircon actually is quite apparent that picks up cerium 4+. And europium can occasionally be found as europium 2+ as well in magmas, and that's going to depend on oxygen fugacity. I'm sure that Michael can go to extreme lengths talking about it. And so these kind of difference in balances can also drastically affect ionic radius and bonding environment. Okay, and this will also, as a result, affect partitioning, and this can generate what we call anomalies in rare earth patterns. So, for example, cerium 4+ and europium 2+ will be preferentially partitioning in zircon and plagioclase respectively, and these can cause negative anomalies in differentiating melts, which are segregating other zircons or plagioclase, for example. Okay, so let's talk about patterns now. Okay, this is what we are here to talk about. And so, yeah, these gradual changes in chemical behavior of rare earth elements can make them very useful geochemical traces, because they can help us actually represent the effect of geological processes and magnetic processes on magmas with using a whole set of elements rather than one or two. Okay, so studied as a group, they can really help identify the wide range of geochemical processes. But we need to find a way to represent it. And then here I've then taken the example of the Anenburg rhyolite, which is a rhyolite from a volcano in the Aleutians. And you can see here that if I simply represent the concentration as ppm on the log scale, we do end up with this sort of sawtooth patterns, which is kind of very hard to read. Broadly, what you could maybe say is that it is actually sort of light rare earth enriched, but because this is straight concentration, it's actually very hard to say. Okay, so it's very hard to identify any meaningful variations in this. So why is that, and how do we get around this? Well, the why is that is actually an issue of nucleosynthesis. Okay, when we look actually the overall distribution of elements in the solar system, what we can see is that overall, there's this suit of sawtooth pattern actually existing for all elements. Okay, it's not just rare earth. So, and this is due to the structure of atom nuclei once again. Okay, and the idea here is that some combinations of protons and neutrons are simply more stable than others. Okay, and more stable configurations are going to be found when the structure of the nucleus is symmetrical. Okay, so even combinations of protons and neutrons, and this is even stronger effects when the number of protons actually is even there. So you can see here, there's a table that I quickly put together with the number of stable nuclei that are found in nature. And you can see here that the vast majority of them are found when we have an even number of protons and an even number of neutrons. Okay, this is due to this more stable nuclei when we have these even numbers of protons and neutrons. Okay, this is what we call the Odo-Arkin rule there. Okay, so how do we get around this then? Okay, but that means that if everything in nature has these sawtooth patterns, then we can start to normalize things to cancel this effect out. And this is essentially what we are doing. Okay, this means that all rocks, fluids, or anything, any geological object or reservoir in the solar system is going to display these typical sawtooth concentrations. So we can cancel this out by normalizing our object of interest or our samples of interest to accepted reservoir values. Okay, whether it's primitive mantle, morbs, shales, whatever. Okay, so here I've represented the Anenburg rhyolite once again, and the primitive mantle composition of Bill McDonough and Century Sun, which is there. And you can see here that these sawtooth patterns are broadly similar in there. They just offset from each other. Okay, so what happens if we start normalizing? Then we end up having these smooth rare earth patterns that are directly usable. And in here, what we couldn't see before is that we have this slight negative europium anomaly that has started appearing. Okay, this is not something we could have been detecting without the effect of normalization. And we do also confirm this sort of light rare earth enrichment here. Okay, so once normalized, these smooth patterns appear and they are ready for interpretation of geogeometric processes. However, there's one little thing here that we need to consider is normalization has implications and it does have geological meaning. Okay, so that means that your normalizing reservoir should be considered very carefully. Okay, so you need to be mindful of which reservoir you use. All reservoirs compositions are going to be derived from a set of samples, a set of averages, and they have a range of assumptions behind them. Okay, so these reservoirs that you use for normalizations are going to be, they're just only as good as the data, the sample set, and the assumptions. And here I've represented again the same highlights to 3 different normalizations. One is the CI contract, so avenite type carbonaceous contracts. This is the composition of Hugh O'Neill, the primitive mantle that I've used in the previous slides, and then finally the NMORB average of Alison Gale, 2013. Okay, and you can see here that although they are broadly similar in shape, actually you could say that the normalization NMORB provide a stronger enrichment in light rare earths, okay, and potentially as well a more pronounced europium negative anomaly. But also they plot at different places in this diagram. Okay. So these are, you need to be mindful of what you're normalizing to. This does have geological meaning. Okay. But also that means that you also need to be careful about what values you use for a single reservoir. Okay. And here I take the example of the carbonaceous chondrites, the CI chondrite values. There's a whole range of values that have been published throughout the last 30 to 40 years. And here, note that I'm not in log scale anymore. These would be simply normalization to the O'Neill CI value, chondrite values of 2016. And you can see here that these differences are not smooth, especially for holmium, we have a whole range of differences. And that means that depending on the values that you're going to use, you could create potential spurious anomalies in your rare earth patterns. So you need to be very careful about this. And it doesn't mean that because one set of values has been used for decades, it means that it still should still be used. You need to be mindful of that, and yeah. So because these can be dramatically affecting your patterns as well. Okay. So now we've talked a lot about the y-axis in these normalization procedures, but actually the x-axis does matter too. Especially we are looking at rare earth patterns, and we're going to be talking about parameterization of these patterns and identifying fractionating phases, or mineral phases that are involved in petrogenesis, for example, or in seawater, for example, or weathering reactions. So when we're talking about rare earth patterns, we talk about the y-axis, but the x-axis is equally as important. Okay, and so typically only extant live rare earths are going to be represented consecutively and equally spaced on the x-axis. This is a typical way of representing rare earth patterns. What if it's not the case? And if we choose a different x-axis? And how can this affect the shape of the rare earth patterns? So the x-axis here, the reason why we choose this kind of representation is that because it represents gradual changes in the chemical behavior of rare earth elements. But in here we said, we have one rare earth that is missing. It's promethium. Okay, promethium is extinct. The isotopes with the longest half-life had the half-life of about 18 years, so it went exit very early on in the history of the solar system. But it should be. Apologies. This is taking a bit longer. There you go. Promethium should be placed here in between neodymium and samarium. Okay, so what if we actually take into account the placement of promethium? Okay, suddenly, as soon as you start leaving the space for promethium and have a true equally spaced x-axis on taking into account the missing promethium here, what you could have here is that your curvature that you had on the light rare earths actually starts to be reduced. Okay, so this does affect indeed the shape of your rare earth patterns there. But what if we even chose a slightly different type of x-axis? And this time, as we said, what eventually what controls the chemical behavior of rare earth elements, at least in a large sense, is the ionic radius. So how about we actually start plotting the ionic radius instead? And what we see here is that if we do this, then we are starting spacing out even more the light rare earth elements, and we do reduce the curvature of these patterns in the light rare earth region. However, we do have the opposite relationship in the medium rare earth and heavy rare earth region, where actually we're starting to compact them. Okay, and this means that there are going to be two effects. As potentially we're going to have a magnification of the europium anomalies by reducing the space between samarium, europium, and gadolinium. Okay, and we're also going to have an increased curvature of the heavy rare earth here from gadolinium to lutetium, the fact that we compact them increases this sort of convex shape here. Okay, so these are caveats that we need to be thought about when you actually start representing rare earth patterns. I'm not going to advocate here a specific set of normalization or specific way of looking at the x-axis. I'm sure Michael will talk about this and at great length in his talk. But I just wanted to highlight these issues in the first place. Okay, so how about 2 quick ways of using rare earth? Here, metal melting, and what we can do is actually identify metal source mineralogy. Here, the partitioning of rare earth elements actually varies between metal minerals, and especially a big control is between spenel and garnet. And importantly, these have 2 different stability fields: lower pressure for spenel, higher pressure for garnet. And importantly, garnet has this very large contrast in compatibility between light and heavy rare earth, with the heavy rare earth actually being compatible in garnet and the light rare earth being incompatible. Okay, and this is especially the case after gadolinium and gadolinium to lutetium, where the compatibility gradually increases dramatically. Okay, and so in spinel, however, it is much less contrasted behavior. And what you can see here is that basalts that are formed with residual garnet, therefore going to have a much steeper rare earth patterns, much more light rare earth enriched and heavy rare earth depleted. Okay, and this is here an example that I took from a paper by Lucy McGee on the Auckland volcanic field volcano basalts. And so primitive basalts here tend to have well and magnesium. You can see that this volcano here, Purchase Hill, have some much steeper rare earth patterns, which is indicating of, especially after gadolinium, we can see this kink here, and this is indicative of a stronger influence of garnet in its metal source, as opposed to Rankitoto, which has more of a spinel influence here. Okay, so stronger influence of garnet, and that hints towards a deeper metal source or a deeper zone of melting, partial melting. Okay, so now we talked about mantle melting briefly. How about fractional crystallization and magma differentiation? So, similarly, rare earth partitioning is going to be widely between minerals involved during magma differentiation. Okay, but phenocrysts, the ones that you can see, the crystals that you can see in the others, may not actually be representative of the minerals involved during the whole scale of magma evolution. And rare earth patterns can actually help unravel these kind of things. So we are going back to the Anenburg volcano here, and I've plotted the whole set of samples from basaltic andesites to rhyolites. Okay, and what we can see is that in most of the others, what we have is actually plagioclase, OPX and CPX, and magnetite. Okay, this is really the bulk of the lavas. So what we can see is that from basaltic andesites to rhyolite, we have the progressive increase in negative europium anomaly. This is very consistent with plagioclase fractionation. Plagioclase is going to take europium 2+ in, it's quite compatible, and going to remove it preferentially over to the 3+ rare earth. So that's okay. However, we know that if you look at partition coefficients from plagioclase and pyroxenes, whether OPX or CPX, it's not going to be able to generate this kind of curvature complex patterns for heavy rare earth elements. What we need here is actually fractionation of amphibole and garnet, and this is the way we can form these kind of shapes in these shapes at the in the heavy rare earth regions. Okay, and these are not minerals that we saw in these rocks. Okay, so this is indeed a cryptic fractionation this time. Hence, the wet magma is differentiating in the mid to lower crust. Okay, this is what these rare earth patterns here can help us unravel that we could not see straight by observation of our hand specimens and thin sections. Okay, this is taken from a classic paper of the late John Davidson. This is the amphibole sponge in the crust here. So this is me sort of done there. I hope that I've put, helped everyone get back to speed on rare earth element geochemistry. Yeah, I'll leave it to Michael to talk a bit more about parameterization of rare earth patterns. Thanks very much.
Super, thank you very much. That was excellent. Just what we needed, I think. So everyone, Marc-Alban has teaching commitments now, so he's going to have to zoom off. I know that there is one question in the chat box, but if that's all right, Casper, we'll ask it in the Q&A after Michael's talk. Okay, cool. Thank you. That was excellent. Much appreciated. See you later.
Thanks very much. Bye-bye.